The Radio Wammo Breakfast.
Yes, talking astronomy now with Dylan Storey, who is an astronomy enthusiast with thanks to the Star Dome Observatory in Auckland City. G'day there, Dylan.
G'day, Wammo. G'day, listeners.
And today we're talking about extrasolar planets. In fact, there's been some discoveries of recent. I gather there's discoveries all the time. But first of all, I guess it would be helpful to know what an extrasolar planet is, Dylan.
Yeah, so extrasolar means it's a planet around another sun than ours. So planets around other stars. And up until 1995, we didn't really know that there were planets around other stars. A lot of people sort of thought there would be because there's planets around our star. But stars are a very long way away, so it's very hard to see these planets, or you can't really actually see them. But up until 1995, that's when the first one was discovered by different methods. And since then, the count as of today is 490 confirmed extrasolar planets.
Okay, and I mean, is that obviously it must be a complicated process in order to actually find these if you can't see them?
You can't see them. It's been I heard it compared to something like trying to see a mosquito crawl across a car headlight between here and Whangarei.
Huh, wow. It's extraordinary.
Stars are very bright, but they're very dim because they're so far away. So to see something that's orders of magnitude dimmer around them is very hard, but there are other ways to detect them. So there are three ways. One way is and the most common way is to detect a wobble, because as a planet goes around the sun, goes around a star, the star's got way more gravity pulling on it, keeping it in orbit, but the planet has a little bit of gravity acting on the star. So that causes it to wobble slightly. And if we monitor the position of that star over a long time, you can actually see and track this wobble caused by a large planet orbiting it. That's one of the ways. Another way is called the transit method, which involves, it's like an eclipsing. It eclipses. So if a planet happens to go in front of the star compared to where we are, then it's going to block out a tiny little bit of light as it goes in front of it. Yeah. That, of course, depends on on that solar system, the plane of it happening to line up with us. Right. So it's pretty small chance, in 360 degrees that it could be on. There's pretty small chance that it's going to happen to eclipse, but still, we have found planets like that.
But so if it does happen that way, I would imagine that would be the easiest way to see one. Or detect one. Yes.
You'd be right there. And you can also pick up the most information about the planet. Yeah. Or more than the wobble method. And it's this transit method I want to talk about a bit more, but I'll just briefly mention the third method, which is called gravitational lensing, which is much more weird, strange, spacey concept. One of Einstein's theories at play, one of these Einstein theories that kind of defies logic and common sense, how space is curved around an object. So if you get two stars or two heavy things lining up in space, the nearer one will essentially act as a big lens in space, curving space around it and acting as a great big magnifying glass in space. And that's called gravitational microlensing. And the research astronomer at Star Dome, Grant Christie, he's been involved in finding some planets using this method.
Wow, awesome.
So, Star Dome's actually contributed to finding a lot of planets this way.
Great.
Anyway, it's the transit method I want to talk about, because there was a spacecraft sent up into orbit about 1.5 years ago. It's called Kepler, and it uses just the transit method. And so what it's done is it's pointed just one small area of sky, a very dense area of sky, towards the thick part of the Milky Way. And its job is just to monitor the millions of stars that can be found in that range over a long period of time. And it's looking for transits. So as a planet comes in front of the star, it's going to block out a tiny little bit of light, and that's what Kepler's there to pick up. And the main goal of Kepler is to pick up an Earth-like planet, because the planets we can detect from those other methods are only ones that are really close to their star and really big. So we're talking about something the size of Jupiter or Neptune, that's orbiting in the orbit of, say, Mercury.
Yeah.
So Kepler really wants to zoom right in and fine-tune its discoveries in a small area of sky and discover Earth-like planets. But if you think of Earth's orbit around our star, it takes a year to orbit around. So that means that Kepler's got to be watching the same star and it's got that dip has to be repeated to be confirmed.
Right.
So it's got to be watching a star for over 2 or 3 years to discover an Earth-like planet.
So therefore, that's quite a resource to stay trained in one area for a long time. So you've got to be sure that you're going to get a result at the end of it.
Yeah, you do, and it's a bit of a gamble, but it's been up there for a year and a half now. I think one of the issues with Kepler, not issues, but one of the things about it is that it's sending vast amounts of information back to Earth, and that information takes a long time to be processed. And of course, with the scientific method, once it's processed, it has to be sent off for peer review, and a lot of different people look at it to confirm the findings, find that there's no anomalies in the data, to confirm that these things can actually mean extrasolar planets. So that takes a long time to chug through, and Kepler had been up there almost a year before the first confirmed planetary discovery was announced, and that was on 4th of January this year, where it found 5 or 6 new planets, sort of some around the size of Neptune. And just recently it's discovered a couple more. And this is a very strange system. It's discovered 2 planets about the size of Saturn, which are orbiting close to their star, but they're gravitationally locked to each other. So as one sets, the other one rises. So as one goes behind the star, the other one goes in front.
Right. Okay. They're almost sort of opposite.
They're almost opposite, yeah. And so this is quite strange, and this actually lends a lot of weight to an alternative theory of planetary formation called core accretion, which I won't go into because it's quite detailed, but
yeah,
it is a bit of a find for the solar system evolutionary scientists.
Great. Well, that's pretty. I mean, that's pretty exciting because who knows? You know, there could be life out on these other planets and these other solar systems. Hey,
there could be, yeah. Not on planets like this because they're too close to the sun. They're too hot.
Right.
And they're too big, so these planets would be gas giants. But again, as Kepler's up there for longer, for a few years, the hope is to discover a planet of similar size, which would have therefore similar conditions and similar distance from the star to have habitable conditions.
Cool.
And there's more stuff you can measure.
Okay, great. What can we see in our own night sky just before we go?
Right. Okay. So we've still got those planets over there in the west. We've got Venus very bright after dark, and Mars is just beside it. So as they sort of move against the backdrop of stars, Venus and Mars they're on a bit of a racetrack at the moment. Venus is just pulling ahead of Mars, but they're still very close together. Saturn is down very low, so you can see it just after dark, and then it will set. And at about 8:30 or 9, we'll get Jupiter rising in the east. So Jupiter is the thing to watch from now on for the next few months.
Good. And if you're in the Auckland region, the best place to go and check it all out, of course, the night sky would be at the Stardome Observatory. Dylan Storey, thanks so much for your time this morning.
Thank you, Wammo, and see you next week.
Will do. Dylan Storey, astronomy enthusiast there, same time every week.